Welcome to example number 2 and a quick discussion of the ideal gas law. Now, in example number 2, we're given an ideal gas in a cylinder that is reduced from an initial pressure of P to a third of that initial pressure, final pressure. And through this process, the temperature is constant. The final volume is 3.5 meters cubed, and we're asked to find what is the initial volume. So when you do ideal gas law type problems, the first thing you do, as we have done in the past with physics problems, is you list your known and unknown quantities. And when you list your known and unknown quantities, you should list them from the two different states. You can imagine that there's a gas initially with some initial pressure, P1, which we'll call P, and then it has a final pressure, which is we'll call that P2, which is a third of that pressure. And then we have an initial volume we'll call V1. We don't know what that is. We have a final volume V2. We do know that is 3.5 meters cubed. And we're told that the temperature T1 and T2 are the same. So T1 and T2 are the same. So when you look at problems, we look at sort of the initial state and list them as P1, V1, T1, and then the final state P2, V2, and T2. But we know that the temperatures are the same, so you could simply call T1 and T2 just T. Another important thing to do when you're doing problems like this is make sure that your units are consistent. Normally we'll be putting our volume in meters cubed, our pressure will be in pascals, and our temperature will be in Kelvin, not Celsius. Remember that the ideal gas law depends on a temperature that is in Kelvin. Okay, now when you look at the ideal gas law, it's really made up from three previous laws. We have the Boyle's law, Gay-Lussac's law, and Charles' law. Boyle's law is when we're looking at a gas and we keep the temperature constant, we find that the pressure is inversely proportional to volume. In fact, this curve that you see here is an inverse curve, and it's what we call an isotherm, you'll see later on, which stands for a process in which the temperature is constant. Thermal means temperature, and iso means constant. In the Gay-Lussac's law, the volume is constant, and so we see that the ratio of the pressure to the temperature is constant, or you could say that the pressure is directly proportional to the temperature in Kelvin. And lastly, we have the Charles law. That's where you keep the pressure constant, and we look at how the volume varies with temperature. And so the ratio to the volume to the temperature is held constant, so hence the volume is directly proportional to the temperature. Now, when you solve ideal gas law type of problems, you could use these individual laws that really build into the ideal gas law. So in recognizing which process you have, a constant temperature, a constant volume, or a constant pressure process. Or you could simply just use ideal gas law and then reduce to one of these forms. Let's take a look at that with this example. So for example number 2, you have a situation where the initial pressure is P and the volume we're looking for, and the temperature is T. And the final pressure is a third, and the volume is 3.5. Now the key fact here is that the temperature is remaining constant. And so this is a constant temperature process, which is really Boyle's law, which you could use this concept that the pressure 1 times volume 1 is equal to pressure 2 times volume 2. And that's because the temperature is constant. However, if you've forgotten this, I personally like to just write ideal gas law written twice. I write PV equals nRT, and then right underneath it I write PV equal nRT, and then I write P1, V1, V2, V2, and then I could write T1 and T2, but T1 and T2 are going to be the same. So we are assuming the gas constants are the same, obviously. The number of moles is the same. We're not assuming that no gas is leaking out of here. So N here and N here is the same. And then we're told that the temperature 1 and temperature 2 are constant. And hence, you get this if you cross multiply. So let's substitute in here. You have P1 is just pressure P. Volume 1 is what we're looking for. Pressure 2 is given as a third of the original pressure. And volume 2 is 3.5 meters cubed. So you can see that the pressures will cancel out, and we have volume 1 is 1/3 of the final volume of 3.5 meters cubed, which gives you an answer of 1.2 meters cubed. And that's it for this example.